let's talk about one of Nikola Tesla's most elegant and honestly just genius inventions, a one-way valve that has absolutely zero moving parts. It's this brilliant piece of engineering that works on pure physics. So let's dive in and see exactly how he pulled it off.
So here's the puzzle at the heart of it all. Think about that for a second. Every valve you can probably picture, the one in your kitchen sink and a car engine, it's got moving parts. Gates, flaps, seals, something that physically opens and closes. So how in the world could you create a one-way street for a fluid using nothing but a solid, stationary piece of material? It really does sound impossible, right?
Well, it wasn't impossible for a mind like Nikola Tesla's. Way back in 1920, he patented something he called a valvular conduit, and it solved this exact problem with an incredibly clever, almost counterintuitive design.
So what is it exactly? Well, a Tesla valve is what we call a passive one-way fluid control device. And that's the key. Its power isn't in some motor or a seal. The entire secret, the magic, is in its internal shape. It's special geometry that's designed to guide the flow one way and, well, to cause absolute chaos the other way.
To really get how this works, we've got to touch on some core physics, because, as it turns out, the direction a fluid is moving can completely change how it behaves. The whole principle of this valve hinges on one simple idea: making one path super easy and the other incredibly difficult.
And this right here breaks it all down. On the left, you've got converging flow. That's where the path gets narrower, the fluid speeds up, the pressure drops, and everything moves along smoothly and efficiently. Easy. But on the right, that's diverging flow, where the path widens. Here, the fluid actually slows down, the pressure increases, and this can create a whole mess of problems, like turbulence and huge energy loss. Simply put, diverging flow is a high-resistance nightmare for a fluid. And that difficulty, that's exactly what Tesla exploited.
Okay, so how did he use this physics principle to build a one-way gate? Let's actually walk through how the design evolves, starting with just a simple pipe, and see how each little change cleverly stacks the deck against flow in one direction.
Here's how it builds up, step by step. First, you just have a simple pipe. Obviously, the resistance is the same no matter which way the fluid goes. But check out step 2. You add a few angled obstacles. Now, all of a sudden, it's a little easier for the fluid to go from right to left. That's converging flow. But it's harder to go from left to right because the fluid has to diverge. Step 3 takes it even further by creating these loops that force any reverse flow to split apart. And by step 4, you've got the final Tesla geometry, which is essentially a maze designed to throw any reverse flow into total chaos. And this is the core strategy, right here. When the fluid tries to go backward, it gets violently shunted into these side loops. The flow just breaks down. The streams collide with each other, and a ton of energy is lost to turbulence. It's almost like trying to run through a maze where every path you take forces you to crash into another runner coming the other way.
To make this even clearer, there's a perfect analogy for what the Tesla valve is doing. It's basically a diode, but instead of controlling tiny electrons, it's controlling fluids. Think about it. An electrical diode is just a one-way gate for current, for electricity. It lets electrons flow forward, but pretty much blocks them from going in reverse. The Tesla valve does the exact same thing, just for water, or air, or any fluid. It's a one-way gate built from nothing but its own shape.
So let's get a little nerdy and look at exactly what's happening to that fluid trying to swim upstream. First, it hits that sudden expansion, the diverging flow we talked about. Then the fluid smacks into these bucket-like structures, which just kills its momentum. It's then forced to do a complete 180-degree turn, which causes even more energy loss. All of this creates chaotic turbulence. And for the final blow, that diverted stream crashes back into the mainstream, causing this destructive mixing. Each stage just piles on more and more resistance.
So this is way more than just a clever invention from history. 100 years later, this exact design has found some really important uses in modern technology. But it's also key to understand where it really shines and, what its limits are. And this chart just says it all, doesn't it? If you hook the valve up in the forward direction, you get a nice high flow rate. But just flip it around, and that flow rate drops dramatically. It's a perfect demonstration of its one-way property, what engineers call its diocity. It's not a perfect 100% seal, but it is a massive reduction in flow. So why is this a big deal? Well, because there are no moving parts. These things are incredibly durable and reliable. They just don't wear out. That makes them perfect for stuff like microfluidics, those lab-on-a-chip devices. They're also used in valveless pulse jet engines, in advanced cooling systems, and even in medical devices where you need flow control that is simple and absolutely fail-proof.
But of course, it's not the perfect tool for every single job. Like we saw in the chart, it's not a perfect seal. A little bit of reverse flow always manages to sneak through. It also works best when the fluid is moving pretty fast. So for anything that needs a 100% airtight seal, a traditional valve with moving parts is still going to be more efficient. But in the end, the real genius of the Tesla valve isn't just in what it does, but in what it represents. It's just solid proof that sometimes the most powerful and elegant solutions don't come from adding more complexity and more moving parts, but from a really deep, fundamental understanding of the physics that governs everything.
And that kind of leaves us with a final thought, doesn't it? This was invented over a century ago by someone who looked at a very basic problem from a completely new angle. It really makes you wonder, what other complex modern problems could we solve today, not with more technology, but by just going back and rethinking the basics?